Throughout industrial history, some machines became so massive, so complex, and so expensive that they didn't just strain budgets, they helped destroy the very companies that built them. These were not ordinary vehicles. They were engineering moonshots, mega-dozers built for foreign governments, 600-foot land trains meant to replace railroads, Antarctic research cruisers rushed into production, and aircraft so huge they could barely leave the ground. Each machine promised to revolutionize mining, construction, warfare, or transportation. Instead, they spiraled into delays, overruns, political conflict, or shifting markets, leaving their creators drowning in debt. What remains today are rusting giants, museum relics, or lost prototypes, monuments to ambition that overshot reality. This is the story of the heavy machines so extreme they bankrupted their makers. The ACO Super Bulldozer, the one-off monster that was too big to sell. The ACO Super Bulldozer is one of the clearest examples in industrial history of a machine that became too large, too specialized, and too expensive for the world it was built to serve. Designed in Italy during the early 1980s, it remains the heaviest bulldozer ever constructed, weighing more than 183 tons, nearly twice the weight of a Komatsu D575A. It was built for a single buyer, the Libyan government, which commissioned the machine to clear vast tracts of desert for major national development projects. With two Caterpillar 3408 engines delivering more than 1,350 horsepower, a blade wide enough to cover a two-lane road, and a massive triple-shank ripper, the ACO was an engineering accomplishment without precedent. Its downfall had nothing to do with its mechanical abilities. In fact, the machine performed brilliantly during testing. What killed it was the geopolitical climate. Just as the bulldozer was completed, international sanctions against Libya came into effect, preventing the shipment of heavy equipment into the country. The ACO Superdozer was suddenly stranded in Italy with no legal path to its intended job site. That moment sealed its fate. Because it had been built for a single, highly specific contract, the machine had no alternate market. Mining companies worldwide were cutting costs, fuel prices were climbing, and no operation wanted a 183-ton one-off dozer with no established parts supply, no transport logistics, and no track record in commercial mining. Moving it from Italy alone would have required dozens of oversized loads, specialized cranes, and an enormous budget that no buyer was willing to consider. ACO searched for alternative customers, but the world simply had no need for a bulldozer of such extravagant proportions. The financial damage was catastrophic. ACO had poured massive resources, manpower, and time into building the machine, expecting a long-term contract. Instead, the Superdozer became a stranded asset that drained the company's finances. Not long afterward, the ACO machinery division collapsed. Today, the enormous bulldozer still sits in Italy, occasionally brought to life for demonstrations. Its sheer size and raw engineering power still able to impress anyone who sees it. Yet behind the spectacle remains a sobering story. The ACO Super Bulldozer was a mechanical masterpiece undone entirely by economics and politics, a machine so large and so specialized that it effectively bankrupted its creators. The LeTourneau land train, the 600-foot gamble that bankrupted a giant. R.G. LeTourneau was famous for machines that redefined the limits of size and power, but the overland land train was the project that pushed even his empire beyond what it could sustain. Developed during the 1950s and 1960s, the land train was a 600-foot-long off-road logistics machine designed to haul freight across remote wilderness where highways and railroads didn't exist. Powered by aircraft-style gas turbines and dozens of electric wheel motors, it was a rolling experiment in extreme engineering. It featured articulated steering, its own living quarters, communication systems, and multiple cargo modules that each carried their own powered wheels. On paper, it was supposed to revolutionize military and Arctic logistics. In practice, it became the financial weight that dragged an engineering giant down. LeTourneau invested immense capital into the land train program, building multiple prototypes and continually improving the design. The C497 overland train, Mk2, was the most ambitious version, stretching nearly 600 feet and powered by 4 massive turbine engines. It was capable, innovative, and in many ways ahead of its time. But as the engineering costs climbed, the military's interest began to fade. New Arctic road networks were being completed. Heavy-lift helicopters had entered service, making off-road convoys less essential. The entire logistical philosophy the land train had been built to support was rapidly becoming obsolete. By the time this shift was clear, LeTourneau had already committed enormous resources. The Army canceled future orders, and the prototypes were placed into storage almost immediately. Without government support, there was no commercial market to justify the machine's extreme cost and complexity. The development expenses were so high that they contributed directly to LeTourneau's financial decline. The company was eventually forced to sell off major divisions, including those responsible for its once legendary earth-moving machines. Today, one of the original land train locomotives survives in Arizona, occasionally started by volunteers. It stands as a towering symbol of visionary engineering that was simply too expensive and too specialized for the world it entered. The land train didn't fail because it was poorly designed. It failed because technological progress made it unnecessary before it had a chance to prove its worth. For LeTourneau, the gamble to build a 600-foot mechanical convoy became the innovation that helped push his company into bankruptcy. The snow cruiser, America's Antarctic mega-project that froze funding forever. Few machines embodied the dangers of overambition and inadequate testing more clearly than the U.S. Antarctic snow cruiser. Built in 1939 under intense political pressure and overwhelming optimism, the snow cruiser was intended to be a mobile science base capable of crossing the harshest terrain on Earth. At 55 feet long and weighing more than 37 tons, it was a massive, streamlined landship equipped with diesel-electric drive, retractable 10-foot wheels, onboard workshops, research facilities, and even a small aircraft stored on its roof. It represented a bold leap into extreme environment engineering, and that boldness became its downfall. The project was rushed from the beginning. Engineers had less than a year to design, build, and test a machine intended to survive Antarctica, one of the most hostile environments on the planet. Funding ballooned quickly, and as the budget climbed, the pressure to deliver increased. When the snow cruiser finally arrived in Antarctica, the problems became immediately obvious. The giant smooth tires, intended to provide flotation on soft snow, had almost no grip on ice. The vehicle that was supposed to roam the continent could barely move across a flat, frozen surface. Even with the tires deflated nearly to the rim, traction remained a serious issue. The crew attempted to use the machine as planned, but the snow cruiser struggled with even minor inclines. Instead of exploring the Antarctic interior, it became a stationary shelter, an expensive one. It served as warm housing and storage, but failed entirely in its intended purpose. The timing was also disastrous. Just as the expedition was getting underway, World War II erupted, forcing the U.S. to pull back its funding and recall personnel. The snow cruiser was left behind, abandoned in the snow and ice. Years later, during a 1958 expedition, explorers rediscovered it in remarkably preserved condition, the tires still inflated and equipment inside untouched. But shifting ice soon swallowed it again, burying the machine somewhere beneath the Antarctic surface, where it remains lost to this day. Financially, the snow cruiser was a spectacular failure. It consumed vast resources, delivered none of its promised results, and became a political embarrassment. What began as a futuristic mega-project ended as a cautionary tale about rushing innovation without adequate testing. The snow cruiser stands today not as a triumph of engineering, but as a frozen monument to ambition that outpaced reality and froze. The big musky, the dragline. So expensive it crushed its owner. Big Musky stands as one of the largest mobile machines ever built by humans, a colossal walking dragline weighing 13,500 tons and towering nearly 22 stories high. Commissioned by the Central Ohio Coal Company in the 1960s, Big Musky was intended to be the ultimate earth-moving weapon, capable of removing overburden on a scale no other machine could match. Its enormous bucket held 220 cubic yards of material, large enough to swallow a two-car garage in a single bite. From the day it entered service, Big Musky became legendary for its power and productivity. But behind that legend was an economic burden so enormous, it ultimately helped crush its owners. The machine cost an astronomical $25 million to build, equivalent to more than $200 million today. And that was only the beginning, transporting the components from Bucyrus-Erie, assembling them on site, and preparing the mine infrastructure added millions more. Big Musky required its own electrical substation, feeding it roughly the same amount of electricity used by a small town. Its maintenance costs were equally extreme. Just replacing the bucket, teeth, or drag cables involved crews, cranes, and budgets that dwarfed the expenses of running normal drag lines. When coal prices were high and demand was strong, Big Musky made economic sense. Its ability to move tens of millions of cubic yards per year offset its staggering operating cost. But as the 1970s gave way to the 1980s, energy markets shifted, environmental regulations tightened, coal demand slipped, and production costs rose across the board. Suddenly, the machine that once symbolized unbridled capability became a financial anchor. Central Ohio Coal struggled to justify its enormous investment as profits shrank. Big Musky required constant, expensive upkeep, and its electrical consumption alone drained company resources. When surface mining restrictions tightened even further, the machine's utility diminished. By the early 1990s, Big Musky had become a stranded asset, a machine too big to move, too expensive to operate, and too costly to dismantle. The company eventually shut down the pit, and with it, their giant. Big Musky was scrapped in 1999, its remaining bucket preserved as a monument. The machine had done everything it was designed to do, but its financial gravity was overwhelming. In the end, the world's largest dragline also became one of the most economically destructive machines ever built, a steel giant whose immense cost helped crush its own owner. The Bucyrus-Erie 4250W, Big Musky's rival, the machine that ended an era. The Bucyrus-Erie 4250W, often called Big Musky's rival, was the dragline that never came to be, and its failure marked the symbolic end of the mega-dragline era. Planned in the 1960s and 1970s, the 4250W was designed to be even larger than Big Musky, with a bucket capacity approaching 250 cubic yards and a structure weighing more than 14,000 tons. If it had been built, it would have been the largest land machine in history. Companies were eager, engineers were excited, and Bucyrus-Erie prepared to build a steel titan beyond anything the world had ever seen. The problem was cost, an overwhelming, insurmountable cost. By the time feasibility studies were completed, the projected expense of a single 4,250-watt had grown to staggering levels. Estimates exceeded $35 million before construction even began, not including assembly, power infrastructure, or ongoing operation. Inflation during the 1970s energy crisis pushed everything higher. Even the largest coal companies balked at the commitment, especially as global energy markets became more unstable. Utility companies, once confident in long-term coal demand, began shifting toward diversified energy portfolios. Environmental regulations tightened, requiring expensive compliance upgrades. Surface mine permitting slowed dramatically. The entire business model that supported ultra-giant draglines began to collapse. In this context, ordering a machine bigger and more expensive than Big Musky was no longer bold, it was reckless. For Bucyrus-Erie, the cancellation was devastating. years of planning, engineering, and sales negotiations evaporated almost overnight. The 4250W represented a major portion of the company's big machine pipeline, and losing it meant losing millions in anticipated revenue. Even worse, the broader market for supergiant draglines evaporated with it. No customer wanted a machine that required its own power grid and carried economic risks larger than entire mining operations. Bucyrus-Erie continued operating for years afterward, but the 4250W cancellation marked a financial turning point, signaling the decline of its dominance in the mega-machine sector. The 4250W never existed physically, yet its shadow looms large. It was the machine so big and so expensive that no one dared build it, and the machine whose collapse helped drag its creator toward bankruptcy. In a strange twist, it became a symbol of ambition that exceeded reality, an engineering dream that helped end the era of world-sized mining machines. The Marion 6360, the Captain, a 15,000-ton Titan that buried its builder. The Marion 6360, known simply as the Captain, was one of the largest mobile land machines ever constructed, a 15,000-ton walking stripper shovel so massive it dwarfed buildings and redefined industrial scale. Built in 1965 by the Marion Power Shovel Company for the Southwestern Illinois Coal Corporation, the Captain carried a 180 cubic yard bucket that could swallow the contents of an entire house in a single scoop. Its boom stretched over 215 feet. Its superstructure towered nearly 20 stories high, and its walking mechanism allowed it to stride across mine sites like a steel colossus. The machine was an engineering marvel, but its price was equally monumental. The Captain cost over $30 million to design, build, and assemble, equivalent to more than $250 million today. Marion poured enormous resources into the project, expecting follow-up orders and a long-term market for ultra-giant stripping shovels. For several years, the investment seemed justified. The Captain was incredibly productive, moving millions of cubic yards of overburden and becoming the pride of Midwestern coal mining. But as the energy landscape shifted, the economics surrounding machines of this size began to collapse. Surface mining regulations tightened, coal demand fluctuated, and power companies broadened their fuel sources. Mines no longer wanted single machines that consumed staggering amounts of electricity, required specialized crews, and created massive single points of failure. The cost of owning and maintaining the Captain was so high that only one machine of its type was ever built, and that was a financial disaster for Marion. Instead of leading to a new generation of mega shovels, the Captain became an isolated Titan with no successors. Marion's investment never paid off. When the U.S. coal industry entered a downturn, the company found itself without buyers for the oversized machines it had prepared to build. Compounding the problem, Marion struggled with increased competition and shrinking profit margins across all divisions. The final blow for the Captain and Marion came in 1991 when a massive fire severely damaged the machine. Repairs would have cost tens of millions, and with coal production falling across the region, the owner chose to scrap the giant rather than fix it. The loss of its most famous machine, combined with years of financial strain, accelerated Marion's decline. Within a decade, the company was absorbed by Bucyrus, ending more than a century of independent operation. The Captain remains one of the greatest mechanical feats in mining history, but also one of the machines whose financial burden contributed to the downfall of the company that built it. A 15,000-ton achievement that literally buried its maker. The Bagger 288 prototype, the bucket wheel gamble that nearly broke Ryan Brown. Before the world saw the final, fully realized Bagger 288, the largest land vehicle ever built, there was its early prototype program, a multi-year experiment that pushed German mining company Rheinbraun to the financial brink. The Bagger 288 prototype wasn't just a machine. It was a gamble of unprecedented scale. Bucket wheel excavators had existed for decades, but nothing of this size had ever been attempted. A 13,000-ton, city-block-long, electrically powered earth-eating colossus capable of moving 240,000 tons of overburden per day. The engineering ambition was staggering, and so was the price. The prototype phase began in the late 1960s, as Rheinbraun sought to revolutionize lignite mining in the Rhineland. Despite success with smaller bucket wheel machines, executives and engineers believed the only way to keep up with post-war energy demand was to build a strip mining machine so enormous it could replace fleets of traditional equipment. The challenge was that no one, no contractor, no manufacturer, no engineer, had ever constructed a machine of such scale. The project demanded new steel alloys, custom-built motors, on-site fabrication plants, experimental control systems, and an electrical feed powerful enough to run a small town. Costs exploded almost immediately, budget projections doubled, then tripled, then became nearly meaningless as the prototype consumed resources at a pace no one had anticipated. Entire sections of track had to be rebuilt to hold the machine during assembly. Multiple redesigns were required when early structural tests revealed dangerous flexing in the superstructure. Even small components, like the buckets themselves, ballooned in cost because they had to be engineered from scratch. By the time Rheinbraun completed the prototype testing phase, the company was drowning in expenses. The machine had devoured tens of millions of Deutsche Marks, far beyond its initial budget, and shareholders began questioning whether the entire project was a catastrophic mistake. Rheinbraun pressed forward only because backing out would have meant writing off years of work, sending morale and investor confidence crashing. In the end, the Bagger 288 succeeded and became a historic engineering icon, but not before nearly bankrupting its parent company. The prototype's runaway costs forced Rheinbraun into aggressive financial restructuring and triggered years of internal scrutiny. The machine worked brilliantly once completed, yet the economic shock of its development haunted the company for years. The final Bagger 288 may be celebrated today, but its prototype phase remains a cautionary tale about engineering ambition. Sometimes, the biggest machine in the world begins life as the biggest financial risk a company has ever taken. The P&H 757 wheel loader, the world's biggest loader that found no buyers. The P&H 757 wheel loader was designed to be the ultimate heavy-duty loading machine, a behemoth so large and so powerful that no competitor could hope to match it. With a 33 cubic yard bucket, a frame the size of a small building, and a weight surpassing 600,000 pounds, the 757 was poised to become the king of mine loaders. But instead of becoming a flagship success, it became one of the most expensive engineering missteps in construction equipment history. A machine so enormous that no one actually wanted it. P&H, traditionally known for its massive mining shovels and draglines, entered the wheel loader market in the 1970s with bold ambition. The mining boom was in full swing, and companies demanded larger and larger machines to load haul trucks efficiently. P&H engineers believed the industry was ready for a radical leap, a wheel loader that could fill the largest mining trucks in only a few passes, reducing cycle times and maximizing productivity. The concept wasn't just to build a bigger loader, it was to redefine the entire loading process. But the market reality proved very different. As the prototype neared completion, costs spiraled. The 757 required custom hydraulic systems, an oversized powertrain, and a frame so reinforced that it drove manufacturing complexity through the roof. Its maintenance needs alone were daunting. The machine was too big for standard shop facilities, too heavy for typical maintenance stands, and too expensive for most mines to justify. Worse, only a handful of haul trucks existed that could actually take advantage of such a massive loader. Mining companies, once enthusiastic, backed away. They deemed the 757 overkill, too costly to operate, too large to transport, and too specialized for an industry already growing wary of high-risk capital spending. Even with excellent performance, the machine was simply misaligned with market needs. As commodity prices softened, budgets tightened, and the appetite for ultra-giant loaders disappeared. P&H found itself with a technological marvel and zero buyers. The 757's failure reverberated throughout the company. P&H poured millions into development, engineering, and prototype testing, only to have the program quietly shelved. The write-off damaged the company's finances and reputation, contributing to the gradual erosion of its dominance in certain mining sectors. Unlike the famous P&H shovels, the 757 became a historical footnote, a giant machine with no market, a masterpiece that never found a home. In the end, the P&H 757 proved a painful truth about mega machines. Bigger isn't always better, especially when the market refuses to follow. The LeTourneau L-2350 early program, the LeTourneau L-2350 in its budget, known today as the world's largest wheel loader, began life as one of the most financially turbulent development programs in heavy equipment history. Before it became a celebrated mining workhorse, the early L-2350 nearly collapsed under its own engineering ambition. The machine was enormous, bigger than any loader ever conceived, with a 53 cubic yard bucket, a 2,300 horsepower diesel-electric drivetrain, and tires taller than an elephant. But the technology required to bring it to life stretched LeTourneau's resources to the breaking point. During the development phase in the early 2000s, LeTourneau faced escalating material costs, shortages of skilled labor, and supply chain pressures from global mining expansion. Every component of the L-2350 had to be engineered specifically for its unprecedented size. The electric wheel motors, the giant articulating frame, the high-capacity cooling systems, and the massive boom linkage all required custom design. Off-the-shelf parts simply didn't exist, driving costs ever upward. Prototyping became a financial nightmare. The first test units revealed structural weak points that required major redesigns. Hydraulic failures, cracking welds, and early drivetrain stress forced the engineering team into round after round of modifications. Each revision added weeks, then months, then entire fiscal quarters to the schedule. Every delay drained the company's already thin budgets. Compounding the problem, LeTourneau had bet heavily on future sales before securing them. The company expected global demand for ultra-class loaders to skyrocket, but mining companies were cautious. Investors hesitated. Buyers stalled. Even those interested demanded guarantees the machine could outperform everything on the market without bankrupting them through maintenance and power consumption. As development dragged on, LeTourneau's finances became strained. The L-2350 program consumed research budgets at a rate the company couldn't sustain. Cash reserves dwindled. Key suppliers demanded payment up front. Internal reports suggested the program's overruns were threatening the company's long-term viability. The L-2350 eventually succeeded, spectacularly. Once perfected, it became an icon of modern mining, capable of loading the largest haul trucks on Earth with unmatched efficiency. But the financial triumph came too late. The massive overrun of the early program contributed to the company's collapse. In 2011, LeTourneau's mining division was sold to Joy Global, now Komatsu, ending the independence of one of America's most innovative machine builders. The L-2350 is now a legend, but its creation nearly destroyed the very company that built it. A reminder that engineering greatness often comes at a staggering financial cost. The Soviet MAZ-7907 land carrier, a 24-wheeler too expensive for the USSR to keep alive. The MAZ-7907 was one of the most extreme vehicles the Soviet Union ever built, a 24-wheeled, 600-horsepower nuclear missile land carrier so vast that it looked more like a mobile bridge than a truck. Stretching more than 90 feet long and weighing close to 200 tons, it was designed to transport and deploy the colossal RT-23 intercontinental ballistic missile. In theory, it was a masterpiece of Cold War engineering, capable of driving off-road, carrying immense weight, and hiding a nuclear payload across the vast landscapes of the USSR. In reality, the MAZ-7907 became a financial sinkhole that the collapsing Soviet economy simply could not sustain. The project began in the 1980s at the height of strategic missile competition. Soviet engineers wanted a mobile launcher so big and capable that it could move a 100-ton missile across fields, forests, and open terrain without relying on fixed bases. This mobility would make the missile harder for NATO to detect. The concept was breathtaking, but the engineering challenges were even greater. No existing truck chassis was remotely capable of handling the load, so the Minsk automobile plant had to design an entirely new platform with 24 independently driven wheels, each equipped with its own electric hub motor. The drivetrain alone cost more than many small military vehicles. The MAZ-7907 used a gas turbine engine borrowed from naval ships, which consumed fuel at a staggering rate. The complexity of the electric drive, hydraulic steering systems, and specialized tires meant the machine needed constant, expensive maintenance. Even during testing, the vehicle suffered repeated failures, overheating motors, cracking frames, drivetrain malfunctions, and electrical breakdowns. Every hour of operation cost the state thousands of rubles in repairs and fuel. When the Soviet economy began collapsing in the late 1980s, the MAZ-7907's cost became impossible to justify. The USSR was struggling to fund basic necessities, and an experimental megacarrier with astronomical operating costs quickly became an easy target for cancellation. By 1991, the MAZ-7907 program was dead. The lone prototype was abandoned for years before eventually being partially restored as a curiosity rather than a practical machine. Although the MAZ-7907 never entered service, its financial impact was real. The Soviet military spent millions developing a vehicle that proved too complex, too expensive, and too difficult to maintain. It became a symbol of late USSR overreach, a grand project built for a superpower that no longer existed by the time the machine was finished. The British Hovercraft SR.N4, the world's largest hovercraft that burned its builders. The SR.N4 hovercraft was once a symbol of bold British engineering, a gigantic air cushion ferry capable of carrying cars, trucks, and hundreds of passengers across the English Channel at airplane-like speeds. When it entered service in the late 1960s, it was the largest hovercraft ever built, a revolutionary machine that seemed poised to transform cross-channel transport. But despite its innovation, the SR.N4 became a financial disaster that drained millions from its builders and operators, ultimately contributing to the downfall of one of Britain's most ambitious engineering sectors. Standing more than 300 tons fully loaded and powered by 4 Rolls-Royce Proteus gas turbine engines, the SR.N4 skimmed over the water at up to 60 knots, far faster than traditional ferries. It could complete a Dover to Calais trip in around 35 minutes. The British public saw it as a futuristic marvel, and the early service runs were successful. However, the machine's biggest strengths became its biggest financial weaknesses. The SR.N4 consumed enormous amounts of fuel, especially during takeoff and rough conditions. Gas turbine engines, originally designed for aircraft, were spectacularly expensive to maintain in a marine environment. Saltwater corrosion was constant, requiring intensive and costly upkeep. Operators soon realized that even with full passenger loads, the hovercraft barely broke even. When fuel prices spiked in the 1970s and 1980s, the SR.N4 became ruinously expensive to run. Meanwhile, construction costs spiraled far beyond expectations. Building one required advanced materials, custom turbines, massive inflation-resistant skirts, and specialized maintenance facilities. The companies behind the SR.N4, British Hovercraft Corporation and later Hoverwork, struggled with massive development debts. Government support was inconsistent, leaving the builders to shoulder much of the financial burden themselves. Over time, these losses helped erode the viability of Britain's once world-leading hovercraft industry. Competition also crushed the SR.N4's business model. As the Channel Tunnel project advanced, it became clear that high-speed rail would eventually dominate cross-channel travel. Even before the tunnel opened, modern catamaran ferries began offering cheaper, more fuel-efficient service. The SR.N4, by comparison, became financially unsustainable. By the early 2000s, the last operational SR.N4s were retired. They had become too costly to maintain and too expensive to operate, despite their impressive capabilities. In the end, the world's largest hovercraft didn't fail because it didn't work. It failed because it worked at a price no company could afford. The SR.N4 lives on today as a museum relic, a reminder of a brilliant machine that bankrupted the dreams of those who built it. The NASA Crawler Transporter program, a machine that cost more than its rockets. The NASA Crawler Transporters, the two massive tracked vehicles built in the 1960s to carry rockets to the launch pad, are among the most iconic machines ever created. Each one weighs 6 million pounds, burns thousands of gallons of diesel per trip, and moves at barely 1 mile per hour. They are engineering marvels, unmatched in size and capability. Yet few people realize that the Crawler program became one of NASA's most expensive logistical projects, consuming more money over the decades than some rocket programs they were built to support. The Crawlers were constructed to serve the Saturn V, the largest rocket ever flown. Moving such a rocket upright required an entirely new class of machine. Engineers designed a platform the size of a baseball infield, mounted on 8 massive tracks, powered by 16 375 horsepower motors. The transporters had to climb inclines, maintain perfect balance, and position the rocket on the pad with millimeter precision. The upfront cost was staggering, over $100 million in 1960s money, equivalent to more than $1 billion today. But the real financial burden came later. The crawlers required constant maintenance to remain operational in Florida's harsh coastal environment. Salt air corroded steel components, hydraulic systems wore down, electrical systems shorted, and tracks needed continual replacement. NASA employed entire teams dedicated solely to crawler upkeep, costing tens of millions per year. These costs continued long after Apollo, even during periods when rockets weren't flying. When the space shuttle program began, the crawlers had to be heavily upgraded. This included reinforced structures, new hydraulic systems, new engines, updated control systems, and specialized jacking platforms. Each upgrade phase cost hundreds of millions of dollars. By the time NASA prepared for the Artemis moon return program, the crawlers underwent their most extensive modernization yet, again costing hundreds of millions. Across 6 decades, NASA spent billions maintaining and modifying these machines, far more than the development cost of several early rockets. For years, internal audits questioned whether building new transporters would have been cheaper than upgrading the old ones, but replacing them was considered too risky. No modern contractor had experience building such enormous vehicles. The crawler transporters are still in use today, carrying Artemis rockets toward the next era of lunar exploration. They remain indispensable, but they also stand as a testament to the hidden price of mega machines. Sometimes the cost of moving a rocket is greater than the rocket itself. The Hughes H-4, Hercules' Spruce Goose, the flying machine that bankrupted a legend. The Hughes H-4. Hercules, better known as the Spruce Goose, is one of the most famous financial disasters in aviation history. Conceived during World War II as an enormous flying transport capable of carrying troops and equipment over submarine-threatened oceans, it became a symbol of brilliant ambition overwhelmed by spiraling costs, political pressure, and the stubborn perfectionism of Howard Hughes. Although it flew only once, for less than a minute, the Spruce Goose consumed so much money and time that it helped push Hughes Aircraft and Hughes's own finances into long-term instability. The idea was bold: build the world's largest aircraft using non-strategic materials, primarily wood, so wartime aluminum supplies wouldn't be diverted. The plan called for a flying boat with a wingspan longer than a football field, powered by 8 massive radial engines. But the engineering challenge was immense. The airplane's wooden construction required entirely new processes, glues, machining tools, and design techniques. Costs ballooned almost immediately. By the time the first major components were assembled, the project had already gone many times over budget. Hughes's perfectionism made the financial hemorrhaging even worse. He insisted on personally inspecting and redesigning parts, delaying construction for months. At several points, he halted work entirely so engineers could retool processes that were already complete. Every change cost money the government no longer wanted to spend. After the war ended, the U.S. military canceled most of its transport megaprojects. The Spruce Goose survived only because Hughes fought Congress and funded the remainder himself. But finishing the aircraft emptied millions from his personal fortune and strained Hughes' aircraft's resources. When the H-4 finally rolled out in 1947, it was a technological triumph, but too late, too expensive, and too impractical to serve any purpose. The plane flew once during a demonstration, lifting to 70 feet for 26 seconds. Hughes claimed it proved the design's potential, but no one believed a wooden colossus that required its own hangar-sized dock could be useful in modern aviation. Operational costs would have been astronomical. Maintenance on its wooden frame alone would have bankrupted any airline or military branch. After that single flight, the Spruce Goose was mothballed in a climate-controlled hangar that cost millions per year to maintain. It drained Hughes' finances for decades, becoming a monument to wasted potential and stubborn ambition. Although it remains an engineering marvel and a beloved museum exhibit today, the H-4 Hercules stands as one of the most expensive aviation failures ever built. A flying machine so costly, it helped bankrupt the legend who created it. The Pelican ULH heavy lifter, the cargo aircraft that never made a dollar. The Pelican ULH ultra-large aircraft was one of the most ambitious and ultimately disastrous cargo aircraft concepts ever proposed by Boeing. Imagined in the early 2000s during the height of the U.S. military's future logistics planning, the Pelican was supposed to be a mega-transport aircraft capable of carrying more cargo than any airplane in history. But before a prototype was ever built, the project's staggering cost, engineering complexity, and non-existent commercial demand doomed it. The Pelican ULH became a financial black hole on paper, draining money from studies and early design phases without ever generating a single dollar of return. The Pelican was enormous even by aviation standards. Boeing envisioned a wingspan of more than 500 feet, twice that of a 747, and a takeoff weight approaching 6 million pounds. Unlike traditional aircraft, it was designed to fly close to the water's surface, using ground effect aerodynamics to save fuel and increase lift. The idea was that the Pelican could carry entire battalions of tanks, armored vehicles, or shipping containers across oceans faster than sea lift but at far greater volume than airlift. The Pentagon was intrigued, but cautious. From the start, the engineering requirements were staggering. A vehicle of that size would need entirely new engines, landing gear systems the size of small buildings, specialized coastal runways, reworked air traffic protocols, and unprecedented structural materials. Even the act of turning such a massive aircraft would require miles of airspace. Boeing's own internal assessments warned that manufacturing costs could exceed those of multiple commercial jet programs combined. And unlike commercial aircraft, there was no civilian market to offset expenses. No cargo carrier, port authority, or shipping company could justify a machine larger than most airports. As cost estimates rose into the tens of billions, military interest faded. The Pentagon shifted focus to modular logistics, precision deployment, and smaller rapid response aircraft instead of massive megatransports. Budget constraints after 9/11 and the wars in Iraq and Afghanistan made enormous experimental projects politically unrealistic. Boeing, already dealing with financial strain in other divisions, quietly shelved the Pelican ULH before the first production tooling could begin. In retrospect, the Pelican was a spectacular vision, an airborne superfreighter capable of reshaping global logistics. But it existed in a narrow space between engineering fantasy and economic impossibility. Without military commitment or commercial buyers, the aircraft had no path to profitability. It never made a dollar, never flew, and never left the drafting table. Instead, it entered the history books as one of the most expensive paper airplanes ever conceived, a brilliant idea that bankrupted itself before it was even built.